So first order system, we had only one time constant to represent the property of the system. Second order system, we'll have two properties, two constants to represent its properties. So second order systems are systems that possess inertia. So there's a mass involved. So such as instruments which are modeled as second order systems are accelerometers, microphones, so for vibration measurement is important, sound measurement, microphones, noise measurement, then earthquakes, etc. Okay, so monitoring signals from there. So any dynamic signals are usually captured using such instruments. So second order systems can be modeled by the differential equation. So second order. So first order was this part. Now we add one more term, A2 d square y by dt square plus A1 dy by dt plus A0 y. This is equal to f of t. So in order to solve this and to reduce it to two constants, we can change it into this form. And the solution is easy. So can be simplified. So 1 by omega n square into d square y by dt square plus 2 zeta by omega n dy by dt plus y is equal to k into f of t. Of course, you might have studied this in mathematics, then dynamics, everywhere. So in the general equation, we had A0 and A2. So now 1 by omega n square equal to root of A0 by A2. So this is called the natural frequency of the system. So why we'll see later. And then zeta is, this is the Greek letter zeta, capital Z in Greek, is A1 by 2 into root of A0 A2. So this is called the damping ratio of the system. So the second order system we have is modeled using two constants, natural frequency and damping ratio. So, okay, so the first part is how to determine. So generally we have to write down the differential equation of the system and then compare it with the standard form to determine what is the natural frequency and damping ratio. So let us do that exercise for two examples. One is strip chart recorder and other is manometer. So strip chart recorder of this type, because you might have seen in various places. I don't know, with the digital instrumentation, this is becoming obsolete. But of course, the hard copy, some places legally they want a hard copy. They don't believe in digital data. So they would like to get a hard copy of the output when it is being taken. So here we have in our surface measuring instrument, we have this sort of a radar, a recorder. I don't know whether I've shown you in the lab class. Okay, so anyway, here we have a pen which is held by a lever, and this moves left and right depending on the signal, proportional to the signal. And we get markings on the paper which is pulled from one side to the other. So we have a roll of paper and it is pulled down. So the mass of this pen is in this and it is subject to a spring force because elastic the fluid between the tip of the pen and the paper. So we can model this system as, okay, is given as in a problem. So mechanically actuated strip chart recording system consists of a plotter head of mass 0.1 kg driven by an elastic belt of stiffness 32.4 newtons per meter with a damping force between pen and paper 10 newton seconds per meter, determining the natural frequency and damping ratio of the system. So we can write down the differential equation of that system in this form. So the pen is the mass. It is acted upon by elastic force from the lever and the friction from the tip of the pen and paper. The mass is acting downward and it is assisted by elastic forces and frictional forces, fluid friction. So the general equation of this system is, okay, applying Newton's law to this mass, mx double dot plus bx dot plus kx is equal to 0. Provided, of course, you are measuring the displacements from the neutral position of the spring. So that mg equal to kx initial. So when you apply or load this spring with the mass, it will come down, and that equilibrium position is taken as the 0 position. Then this will be the differential equation of the system. Okay, I think you would have studied this in many places. It's a famous differential equation. So the solution, okay, to our problem is, so we have to compare this differential equation. So omega n equal to root of a naught by a2. So a naught, this is a2, m is a2, a naught is equal to k. So omega n equal to root of a naught by a2 is root of k by a. So substituting the values, we get 18 radians per second. When zeta equal to a1 by 2 into root of a naught a1, a naught a2. So v by 2 into root of km is equal to, substituting, we get the corresponding values. Okay, so thus we can determine. So by comparison, so by writing down the differential equation of the system and then comparing with the standard form, we can determine the natural frequency and damping ratio of the system. Okay. So any question? Okay. So another problem, determine the natural frequency of the U-tube manometer, neglecting viscous friction and considering viscous friction. Okay, so U-tube manometer, suppose you are using to measure a dynamic signal. So what will happen? Say a pressure change. So pressure is fluctuating. So sometimes unknowingly you might have observed it in the lab, fluid mechanics lab, that the manometer goes up and down when you suddenly switch on the pump or something like that. So how do we determine the natural frequency of the U-tube manometer? So the U-tube manometer can be represented as a mass of mercury in a U-tube. The tube has a radius of r. So this mercury can go up and down. So suppose it has moved by a distance x from the equilibrium position, then so the driving force towards the equilibrium position is, so the mass of this extra mercury column is what which tries to drive it up. So that is given by, so area of cross section is pi r square into x is the volume of this portion. So plus the volume of the portion. So 2 pi r square x is the mass of this column of mercury. Okay, so that is this part. So that is the volume. Volume into density will give mass, and the force acting downwards, you have to multiply by g. So this is the the elastic force, the restoring force, and the inertial forces are given by this. Total mass is pi r square into L, the total mass of the system. The whole thing moves up and down. So pi r square L into rho is the mass of the system, total mass of the mercury in the U-tube. So mass into x double dot is the is the corresponding term because of the inertia of the mercury part. So now we have to convert this into standard form and natural frequency and ratio. So the timing ratio is not there. We cannot find the timing ratio from this equation. So the natural frequency is root of n0 by h2 the friction force is not easy. So we can use for simple cases laminar flow, etc. Based on viscosity of the mercury, etc. So there is we can find it solved in the book by Doblin, page 490. Two pages. Uses both. First, it starts with the laminar flow and then goes for turbulent flow also. Uses an approximate equation to represent the friction forces in turbulent flow. Okay, so that is how we can determine natural frequency of a system. So we have to write down the differential equation after seeing the forces which are acting on the system and then find out omega n and zeta. So that is the general part. Now we come to the specific part. First is, suppose we are given a